Okay, I had a question about chapter 14, number 45. Let's take a look at that one here. And the natural oxidation of hydrogen sulfide released by decaying organic matter. And so he burned hydrogen sulfide to create oxides of sulfur, like sulfur dioxide, or sulfur trioxide. So they give us the reaction 2H2S. Gas plus 3O2 gas yields 2SO2 gas plus 2H2O liquid. How many milliliters of hydrogen sulfide measured at 19 degrees C at 549 torr will be used in the reaction that also uses 704 milliliters of O2 at 159 torr at 26 degrees C? All right, this one's complicated because we have different temperatures and pressure for both of these. And so there are two ways we could do this one. One way is, we could just say 744 milliliters of O2 will require a certain number of milliliters of H2S. Then we'll have to change it. And so we could do the Avogadro's, milliliters to milliliters conversion. Or we could just do it stoichiometric way, the standard mole-to-mole conversion. And so what do you prefer, doing mole-to-mole conversion or milliliter to milliliter conversion?
The one like T1, V1 over T1.
Well, let's just do a mole-to-mole conversion here because, and so if we have 704 milliliters of O2, 704 milliliters of O2 gas, and the O2 gas is going to be at 159 torr and 26 degrees C. So we can go from volume of O2 gas to moles of O2 gas. And then from moles of O2 gas, we can go to moles of H2S gas. And then from moles of H2S gas, we can just go to the volume of H2S gas. Yes. Okay, rather than doing the other way we could do it is we could just do it from milliliters of O2 to milliliters of H2S using this as a volume ratio. And then once we have the milliliters of this, we're going to have to convert it to the correct pressure and temperature. So the volume of H2S, the only reason this gets screwed up is because the volume of H2S is going to be at 19 degrees C and at 549 torr. And so otherwise it'd be very simple volume to volume conversion. So the other way of doing this would be here. 2H2S gas plus 3O2 gas. This yields the other stuff here. And so what we do is we go from 704 milliliters of O2 to milliliters of H2S. Here the ratio would just be a 2 to 3 ratio. 2 milliliters of H2S for every 3 milliliters of O2. But the problem is this is going to be at the same temperature and pressure. So this is going to be at 159 torr and 26 degrees C. And then what we'll have to do is we'll have to do a combined gas law. That is, we'll have to do one of these P1 V1 over T1 to equals P2 V2 over T2 type deals. And then we'll have to solve for V2. So V2 is equal to P1 over P2, T2 over T1, V1. And, those are the two ways you do it. Do you want me to do it one way? Which way? The second way? start off here with 704 milliliters of O2. Chapter 14 is on the test, but chapter 15 we'll probably not put on this test. Keep the material down a little bit. Although we're almost finished with chapter 15. So 704 milliliters of O2. And then what we'll just do is we'll do this. This I'll call it T1, P1. Okay, and then we'll just use this conversion factor that is the 2 milliliters of H2S for every 3 milliliters of O2. And so what does that come out to? So 704 times 2 divided by 3 equals 469. 469.3 milliliters of H2S at T1, P1. Okay, but we're going to change the temperature and pressure now. And so, that's going to equal how many milliliters of H2S at T2, P2. And so here we can't do a dimensional analysis. Here we are going to have to do an algebraic equation. And so what we'll just do is we'll just figure out this is V2. V2 is equal to P1 over T1. P2, sorry. P1 over P2. T2 over T1 times V1. So P1, we'll just get off there. So the O2 was originally at 159 torr. P2, we're going to go up to 549 torr. So the volume should shrink. Torrs cancel here. Like 1/5 the volume because the pressure increased about 5-fold, less than 5-fold. T2 over T1. T2 is 19 degrees C, so 19 plus 273 would be what? 19, 280, 292. 292 Kelvin. Is that right? Yeah, 292 Kelvin. T1 is 26 degrees C, so that would be 299 Kelvin. And so if we increase the temperature, the volume should expand or contract. If we increase the temperature, the volume should expand. So you know what? I must have gotten these flipped because this is going to decrease. This is less than 1. It's not going to increase. So T2 is 299 Kelvin, and T1 is 292 Kelvin. Times V1. V1 is 469.3 milliliters. So all we're doing is we're going to take our H2S and increase the pressure. If we increase the pressure, that's going to decrease the volume. And then we're going to increase the temperature a little bit. Increasing the temperature a little bit expands the volume. But the pressure increase is significant. The temperature increase is not that significant. And so I expect the volume to be smaller because of this. So V2 comes out to, let's see, comes out to I just cleared my calculator, unfortunately. 469.3 times 159 divided by 549 times 299 divided by 292. 139.1. So the first part is with stoichiometry. For for every 3 liters of O2, we're going to consume 2 liters of H2S. And so this is how much H2S we need under those particular conditions. We're going to need 139. It's at a higher pressure. That's why, pretty much. Okay, does that answer the question? Let's see how the book did it.
I mean, I don't understand the second
They
part.
skipped a step. Well, actually, they didn't skip a step. They did it the opposite way. What they did was they did this. They changed the O2 first. And so, you know, what they did with the O2 is that's 704 milliliters of O2 at 159.4. But if you increase the pressure to 549.4, it shrinks. So this is what they did. They shrank the O2 because of the higher pressure. And then they're going to increase the temperature. They increase the temperature, then well, actually we decrease the temperature. I screwed it up. We're decreasing the temperature. Made a mistake. I thought we were increasing the temperature. We're actually decreasing the temperature. This was right, 292 over 299. So decreasing the temperature shrinks the volume, increasing the pressure shrinks the volume. Both of these factors are less than 1. And so that comes out to, 133. 133. So what they did was they got 199 milliliters of O2 at P2.
I got
T2.
the first part, but the second part.
Oh, that's because that was O2. Now, for H2S, we need 2 liters of H2S for every 3 liters of O2. So this is the stoichiometry. And so that's just 199 milliliters of O2. Okay, does that make sense?
Yeah.
All right, are there other questions? Shima, you said you have a lot of questions? Yeah, let's go through your questions.
So, chapter 10, 83.
Chapter 10, 83.
Also 83.
How do I get back? I can't go backwards in this. It's really weird. So I have to log back into Cengage. Number 83. Let's do number 33 now. Fluorides retard tooth decay by forming a hard acid-resistant calcium fluoride layer reaction. We've got tin 2 fluoride plus calcium hydroxide yields calcium fluoride plus tin 2 hydroxide. What kind of reaction is this? Yeah, double replacement. Driving force would be precipitation of calcium fluoride. If at the time of the treatment there are 239 milligrams of calcium hydroxide on the teeth, and the dentist uses a mixture that contains 305 milligrams of tin 2 fluoride, has enough of the mixture been used to convert all the calcium hydroxide? If no, what minimum additional amount should have been used? If yes, but what number of milligrams was the amount the next? So what we have here is a limiting reagent problem. So we're given the two reactants, 305 milligrams of 2 fluoride, 239 milligrams of calcium hydroxide. So how do we do the limiting reactant type problem? First step is to Well, actually, this was a general overview of how we're gonna solve this problem. How we're solving this problem is the first part of solving this problem is to determine what? How do we figure out the limiting reagent? What's the strategy we're gonna use for it? Smaller amount. So we gotta figure out, first we gotta figure out the, what? In the smaller amount method, step one was what? Determine the yield although this the comparison of moles method would work pretty well for this particular problem, but we'll just stick with one method. And so we determine the yield from what? How many people got this problem? 83. How did you guys do it?
239 milligrams and 5 grams of
Okay, so you did a comparison of moles. You said 239 milligrams of calcium hydroxide required what?
4.
So you went from calcium hydroxide to tin 2 fluoride?
Yeah.
Okay, so that's called comparison of moles. What you could do is you could go 239 milligrams of calcium hydroxide needs how much tin 2 fluoride, and then see if you have enough or not. And so how much was it?
It was 505 milligrams.
505. Did we have enough?
No.
No, so that's comparison of moles. I didn't do comparison of moles. I did the smaller amount method. Smaller amount. The reason I like the smaller amount method is because oftentimes we want the theoretical yield of product here. And so, if no, what additional amount do you need? You would need, yeah, 200. And so that would be the fastest way of doing it. But the way, yeah, that's fine. That's a good way of figuring it out. So we got to pick one or the other. It's a 1-to-1 mole ratio. And so over here we have 239 milligrams. And so we go to moles here, and then from moles we go to moles here. And then we can figure out how many milligrams here required. Or we could have started off with 305 milligrams here. Calcium hydroxide. We go to moles here, and then figure it out how many milligrams here. This is comparison of moles. The other way we could have done this is the way we did the other limiting reagent problems. The way we did the other limiting reagent problems was by the smaller amount method. It would have been a little bit longer of a calculation, but you use the same method, over and over, so you build or reinforce that method. Would we get a negative number? No. This is so how many milligrams did you get from this one? 505?
Yeah, 505.
Hmm?
505.
505? 505 milligrams required, and we didn't have enough. We only had 305, so 250 milligrams extra were needed. Okay, if we did the comparison of moles method, we wouldn't have gotten a negative number. Just it's a longer calculation, that's all. And so for comparison of moles, we calculate the yield one is the yield of, then pick one. We'll pick calcium fluoride. It's not specified. The calcium fluoride is the main product. Tin 2 hydroxide is not. So we'll just pick the calcium fluoride and then do the yield from 305 milligrams of tin fluoride. So we go 305 milligrams of tin fluoride. Eventually we'll get to moles of tin fluoride, then to moles of calcium fluoride, and then to milligrams of calcium fluoride. And then two, we'll do the yield of calcium fluoride from 239 milligrams of calcium hydroxide. So here we'll just go moles to moles of calcium fluoride to milligrams of calcium fluoride. And then compare the two. Which of these two should be smaller based on your earlier calculation? Based on the earlier calculation, it looks like the tin was the limiting reagent. It's the limiting reagent here. And so what we would do from there is, if tin is the limiting reagent, we could figure out the amount of excess reagent that remains, which would be the calcium hydroxide, and then figure out, based on how much excess reagent remains, we can calculate how many additional grams of tin 2 fluoride are required to react with that. And so it would be two more calculations, or we could do the other alternative that you did there. And so either way, this would be a longer calculation of doing that. No? But did you want me to do it, or want me to do this way? All right. Do it this way then. There are actually many ways we can solve these problems. So let's take a look. All right, in general, I'll just solve it the same way and then look at branches based off that. So we'll do the first calculation, 305 milligrams of tin 2 fluoride. And then I just converted to grams. I don't like millimoles, and I don't like the milli for the mass either. I just like to go to grams. And so this is 1,000 milligrams per gram. That gives me grams of tin 2 fluoride. What's the molar mass of tin 2 fluoride? Molar mass. What did you get? 150. 156.7. 156.7. 0. Grams per mole. So grams cancel, milligrams cancel, we're left with moles of tin 2 fluoride. And then we have the mole ratio. So just a 1-to-1 mole ratio. So 1 mole of calcium hydroxide, or actually we're going to product. 1 mole of calcium fluoride for every 1 mole of tin 2 fluoride. And then we're going to go to mass. You probably didn't calculate the calcium fluoride mass, or maybe you did. Did you? 74.10 grams per mole. Thanks. If you're good, if you're good at calculating molar masses and you don't need any more practice, the easiest way to get it is just from Wikipedia. And so if you want to save time doing your homework, you can just go to Wikipedia, and it's always going to give you the molar mass. Here, the molar mass, 78.07. So that saves you time if you already know how to do it. If you need more practice doing it, then you should do it. And the other advantage of doing it and getting more practice is you learn the molar masses. If you just always look it up, you don't see those molar masses that much.
I accidentally gave you the wrong molar mass. That's not a. I accidentally gave you the molar mass of calcium hydroxide.
Oh, okay.
That's my bad.
Okay, that's okay. So 78.07. And then we'll just go to milligrams, 1,000 milligrams per gram. And so moles of tin 2 fluoride, moles of calcium fluoride cancel, grams of calcium fluoride cancel, and then we're left with milligrams of calcium fluoride. Thousands cancel. So let's go ahead and do the calculation here.
Professor,
Yeah.
on the test, is it okay to do calculations for millimoles and milligrams for kilomoles and kilograms?
You can do that, that's fine. You want to do that. So I got 305 divided by 156.7 times 78.07. 151.9. All right, so the reason, there's another reason I don't like comparison of moles. The other reason I don't like comparison of moles is because oftentimes we want the theoretical yield, and so that's another part of the calculation. And so if we do comparison of moles, then we'll, then it makes calculating theoretical yield longer. And so it's a trade-off, one or the other. Or if you do both, it's fine. If you know which one to do, then that's the best. 239 milligrams of calcium hydroxide. So again, I don't like to do the milli stuff. Just go straight. What's the molar mass of calcium hydroxide? Okay, yeah, 74.10. Grams, milligrams cancel, moles of calcium hydroxide. All these are 1-to-1 moles ratios. So even though they're 1-to-1, we still have to put this in here, otherwise it doesn't cancel. Make sure everything cancels. 7807 grams of calcium fluoride mole. Calcium fluoride, and 1,000 milligrams per gram. So, what do we got? We have 239 divided by 74.1 times 7807. 251.8. 251.8 milligrams of calcium fluoride. And so the smaller amount method, this is the theoretical yield. It's a smaller amount. Okay, and this will be the limiting reagent. This will be the excess reagent. Now the limiting reagent is completely consumed. So getting back to the problem here, okay, has enough of the mixture been used to convert all of the calcium hydroxide? No. We're going to have excess calcium hydroxide remaining. If no, what minimum additional amount should have been used? If yes, by what number of milligrams of the amount in excess? And so the answer is no. And so what we need to figure out is how much more tin 2 fluoride do we need? And so since I did it this way, now we can figure out, well, how do we figure it out? What would the easiest way there be? Okay, so the easiest way would be something like, okay, this is not the easiest way, but this is the way we do it. amount of excess reactant remaining. The reason I'm doing it this way is because this is our standard calculation. These are our standard steps in the limiting reagent problem. And so the amount of excess reactant remaining is equal to 239 milligrams of calcium hydroxide. And then we're going to go to minus the amount consumed by the LR, limiting reagent. And so that's 239 milligrams. And how much was consumed by the limiting reagent? Well, the limiting reagent is 305 milligrams of tin 2 fluoride. So we'll start off with that. 305 milligrams of tin 2 fluoride. And then convert this to grams. And then we'll go to moles, 156.70 grams per mole. And then from here, we're going to go to moles of calcium hydroxide. Milligrams of calcium hydroxide. And so it's a 1-to-1 mole ratio, 1 mole of calcium hydroxide for every 1 mole of tin 2 fluoride. And then we had the molar mass of calcium hydroxide from earlier, 74.10. 74.10 grams per mole of calcium hydroxide. And then we'll just convert it to milligrams here. So 1,000 milligrams per gram. So it'll give me the number of milligrams of calcium hydroxide consumed by the limiting reagent. And so it's 305 divided by 156.7 times 74.1. 144.22. So it's going to be 239 milligrams minus 144.22 milligrams of calcium hydroxide. Minus 239, 94.7. So it's going to give me 94.7 milligrams of calcium hydroxide unreacted. All right, so this is our basic, this whole thing is our basic limiting reagent calculation. Now we got to do one extra step to this. The one extra step that we're going to do is figure out, well, if I want to react this excess, how much additional tin fluoride do I need? Tin 2 or stannous fluoride do I need? And so this is an additional calculation. On top of our standard calculation. And so the extra calculation is we have 94.7 milligrams of unreacted calcium hydroxide. And this is going to require, how many milligrams of stannous fluoride or tin 2 fluoride to react that with that excess. And so one final stoichiometry calculation is just going to be 94.7 milligrams of calcium hydroxide. And then we'll convert it to grams. And then from grams, we'll go to moles, so 74.10 grams per mole. And then we'll just go to moles of tin tin-2 fluoride. It's a 1-to-1 mole ratio. 1 mole of tin-2 fluoride for every 1 mole of calcium hydroxide. And then we'll convert that. What was the molar mass of tin-2 fluoride? 156.70 grams of tin-2 fluoride per mole. Fluoride. And then we'll convert it into milligrams, 1,000 milligrams per gram. The reason I don't use the kili or millimoles and all that other stuff is I keep the core the same. The core of this is always looks the same. Gram to mole conversion, mole to mole conversion, that type of thing. It's always the same. And so anyway, I have this in my calculator with all the digits. So I'm not going to round it. I'm just going to use all the digits in the calculator because I didn't clear it. So it's 94.77217613 is what I have in the calculator, divided by 74.1. The reason I keep all the digits in the calculator is to minimize round-off error, times 156.7 equals. And so this comes out to 200.4 milligrams of tin-2 fluoride required. So an additional 200.4 milligrams of tin-2 fluoride is required to react with the excess that remains. Does that make sense?
Yeah.
Okay, so that's the way I would have done it. Even though this took about this probably took about 5 times longer than your guys' method, but the thing is, it's just the same methods. But work on mastering the same, and then start branching off from that, and then you can see shortcuts. Like I said, there are many ways of solving these problems, and I can start introducing a lot of shortcuts. Millimoles, kilimoles, this kind of stuff. But even though it takes longer, you have too many ways of doing it. Sometimes it's confusing, in the longer run, and so sometimes slow but steady is better than fast. Quick. Sometimes. All right, other questions?
Can we go over the sample test?
Which one in the sample test? If you have specific ones, we can.
On number 56 on chapter 10.
Number 56, chapter 10. Burning sucrose transfers 3.94 times 10 to the third calories per gram to the atmosphere. Calculate the amount of energy in kilojoules transferred when 56.7 grams of sucrose is burned. 56.7. So this is the way we would do this is just by dimensional analysis. We wouldn't necessarily have an equation to do this. We just look for conversion factors. So the fixed amount is 56.7 grams of sucrose. And so what we'll do is we'll just look for something that gets rid of grams of sucrose or grams. We actually have something that gets rid of grams of sucrose. And that is, there's going to be 3.94 times 10 to the third calories for every 1 gram of sucrose. So the grams of sucrose would cancel out the grams of sucrose. And then we need some additional ones. The additional ones would be given. You don't necessarily have to memorize it. This is 4.18, actually, or 4.184, depending on what the book does. Does the book do this to 3 sig figs or 4 sig figs? 4.184 joules per calorie. And so what we could do here is we get rid of calories, convert it to joules, 4.184. joules per calorie. The calories cancel. And then we'll go to kilojoules. 1 kilojoule is equivalent to 1,000 joules. And so this should do it for us. Here, we burned the glucose. So 56.7 times 3.94 times 10 to the third. Times 4.184 divided by 1,000. 34.6. 934.6 kilojoules are released to the atmosphere. In fact, all these energy and stoichiometry problems are dimensional analysis types, so you're always looking for conversion factor. The conversion factor is going to be given in different ways. Like if we look at this one here, 5.8 times 10 squared kcals of heat is transferred out of the body by evaporation per day. So the conversion factor here is 5.8 times 10 squared kilocalories per day. Now they want to know in a year how much. And so in a year, that's the fixed, and then the conversion factor is this, 5.8 times 10 squared kilocalories per day. Here are 333 calories. The list of the calorie content of foods indicates that a piece. So this would be 333 calories per slice of pie. And so those are the types of things we're looking for. We're looking for conversion factors, so we can do this using dimensional analysis here. This one, the conversion factor here is, this one's going to be 493 kilojoules per 15 grams. So for every 15 grams of carbon, we get 493 kilojoules. So we write this 493 kJ over 15 grams, or 15 grams over 493 kJs. That would be a conversion factor that we use in dimensional analysis. But what they want us to do here is not do a dimensional analysis. We are doing, we're just converting kilojoules into calories and kilocalories. Unit conversion there. But when we're doing a problem like that, this earlier one we do. Here is another conversion factor of 2.82 times 10 to the third kilojoules per mole of sugar formed. So, sugar being C6H12O6. All right, other questions? No other questions? If you have a specific question on the test, you can, but practice test is meant for practice, you know, so you want to try it first before somebody gives you all the answers, because if somebody gives you all the answers, then I'm just repeating what I'm doing every day, and like every day we're doing problems, I'm just giving you the answers, right? And so you want to take a different approach with it.
I have a question about electron configurations. Not from the homework, but why is it that, so I know that each group has a different charge on it, but why is it that the electron configuration is like less than the number of electrons? Is that because of that charge?
The electron configuration can be more or less.
Right, but why, in the examples from the slideshow, it's never the exact number, it's never the atomic number.
For ions?
Yes.
Ions, it can't be, because ions are going to either have extra electrons or they've lost electrons.
So then how would you know which would have extra and which would have lost?
Cations would, I mean, if it has a positive charge, cations have lost
And anions.
have gained.
But if it just says ion.
If it just says ion, like if it just says ion, then it can either be lost or we don't know. If it just says ion, it could be less or more. You know? If it gives you a name, then we can figure it out.
Okay, but if it just says like calcium ion.
Oh, then we know, because calcium ion, you know the charge of calcium ion. What is the charge of calcium ion?
2 plus.
Yeah, and so it's lost 2 electrons. So you would know that calcium ion is formed from calcium metal. Calcium metal goes to calcium ion plus 2 electrons. This is
Okay.
redox style thing. And so, well, if it's lost 2 electrons, then calcium metal has electron configuration. We could just get it from the periodic table. You know, the nearest noble gas to calcium is argon. So we'll start on argon, number 18, and then just add 2 electrons to that. So if we start off with the nearest noble gas, we'll go argon for the core, and then what's the S?
What's what?
What's the S? What row of S is that? 1S, 2S, 3S, 4S? What's the S? For calcium. 4S. And then 4S2. So this is 20 electrons. Now calcium 2 plus must have 18 electrons, because 18 electrons plus 2 electrons is going to give me 20 electrons. So what is calcium 2 plus's electron configuration? It's got to be argon, because we must have lost these 2. So it's got to be 4s0, because there's no more 4s electrons in there. So we know that. And so basically, if it says ion, we don't know unless they give us a name. If they give us a name, then we can figure it out, because we're supposed to have all the charges memorized, basically. Then we can determine if it's lost or gained. Okay, other questions? If there's a, Shima, did you work on the practice test? Do you have a question about particular ones?
Number 3.
Number 3? The 111 orbital is forbidden. Is it true or false? It's false. False. Why is it false? All right, 111 is false because of the violation of Schrodinger's equation. This is not a solution to the Schrodinger equation because of because of first one? No, it's because of the second one. What's the problem with the second one? The problem with the second one is that it's too big. You can't have that big of an L value. It's not allowed. It's what we call forbidden. What is the biggest L we can have? What is the biggest L that is allowed? In this case, it's n minus 1. Well, n minus 1 is 0, so the biggest L we can have is 0, so this violates that. M is not in violation. M is okay. If L is equal to 1, we can have an M equal to 1. And so that just deals with the rules for quantum mechanics. The rules for quantum mechanics, the rules for the quantum numbers, you just have to have those memorized. If it doesn't conform to the rules, then it's forbidden. If it conforms to the rules, then it's allowed. That's basically it. So this is forbidden. Uh-huh. Okay, well, what it stands for is, what I was asking for on the quiz thing was the, what does it represent? What does M represent? what M stands for is called the magnetic quantum number. And the magnetic quantum number, when you put these atoms in a magnetic field, then in this something called splitting that happens. But we don't care about. The magnetic quantum number is just some abstract name that's placed on there. But what does it represent? What it represents is the number, the number of unique values of M are the number of orbitals in that sub-level. L we call a sub-level, and M's going to have a number of unique numbers. So for example, if L is equal to 2, we have 5. Unique numbers, 2L plus 1. And so what M represents is the number of orbitals and their orientation for each sublevel. For each L, we're going to have different numbers of orbitals, varying from 1 on up to huge.
So to find your M, that's the equation like 2L plus 1.
2L plus 1. 2L plus 1 tells you the number of orbitals. 2L plus 1. And so a question might be like this. Z. Have you ever heard of the Z orbitals? In the Z, or how many Z orbitals? It's like how many p orbitals are there? How many p orbitals are there? And let's say 3p. How many p orbitals do you have? 3, yeah. In the 3s, how many s orbitals are there? 1. 3d, how many orbitals are there? 5. Okay, so what I'm going to do is I'm going to do this. I'm going to say let's say in the 99z orbitals. Okay, first off, are the 99z orbitals allowed or forbidden? 99z orbitals allowed or forbidden? Why don't you tell me? Just sit there and see how fast you can answer this. Are the 99z orbitals allowed or forbidden? First group to figure it out, or first person to figure it out, will win a bonus point. Hmm? I know what you're saying. What you're saying is what a lot of people say, but it's not true. Hydrogen. Hydrogen has 1 electron in the ground state, right? So this electron would be a 1, 0, 0, 1/2 electron right here. So is the 1, 0, 0 minus 1/2 electron allowed or forbidden? Is that allowed or forbidden? How about a 2, 0? If I have a 1s orbital for the hydrogen, is a 2s orbital allowed or forbidden for hydrogen? Is a 2s orbital allowed or forbidden? Well, there's no electron in there. If there's no electron, it must be forbidden, right? If there's no electron in there, is it forbidden? Or is it allowed? It's allowed. It's allowed. 2s orbitals allowed. 2p orbitals are allowed. 3s orbitals allowed. All those orbitals all the way up to infinity are allowed. Just because they don't have any electron in there doesn't mean, it's not allowed. It's allowed. If you can get an electron excited enough, actually we can excite an electron. We can excite an electron from the n equals 1 to the n equals infinity. When we excite an electron from n equals 1 to n equals infinity, that's called ionization. And the amount of energy that requires is the first ionization energy for hydrogen, which is about 2,200 kilojoules per mole of hydrogen atoms. So it's easy to do. We can excite the electrons up to higher energies, or in between. This is why hydrogen emits. How does hydrogen emit the red light? how hydrogen emits a red light is an electron gets excited to the third level and drops down to the second level, but all those levels are loud. How does hydrogen emit UV? Hydrogen can emit UV, it just gets excited to higher energy levels and makes a bigger drop. That's it, but all those are loud. Now, just because the elements only occupy up to the, if we look at it, this is the 4F, this is the 5F, this is the, this 1, 2, 3, 4, 5, 6, 7. So we fill up to the 7p, that takes us to 118. So 7p, does that mean nothing exists after 7p? No, there are a bunch of empty orbitals that exist, and those are just allowed or forbidden. So it's the same kind of thing. I know our book starts talking about it. Our book starts talking about the periodic table only fills to 7p, so a lot of people ignore the higher energy. If you ignore the higher energy states, then you aren't going to be able to ionize anything. You aren't going to be able to emit UV. There's something called, I was watching, what was I watching? Oh yes, I was watching, have you seen that? Making a Murderer? Netflix? Making a Murderer? Kind of interesting. They're doing some, they're looking at some samples under electron microscope, and what they can do is they can shine photons at a sample, and what was it? I think it was a soil sample or something. I forgot exactly what it was. And then they could get the elemental composition. How they do that is they knock electrons out of there, out of the inner shell. They can knock electrons out of the inner shell, then outer shell electrons can drop in. When the outer shell electrons drop in, they start emitting X-rays. So elements have a characteristic X-ray spectrum, and that X-ray spectrum is used to identify elements. So they were looking at calcium. Calcium and bone fragments. They were looking at bone fragments, and so a bone fragment should contain calcium and phosphorus. And so they had these things that kind of look like bone fragments, and they're going to analyze them. And what they found was there's a signature for calcium, but not calcium and phosphorus. You need calcium and phosphorus to be a bone fragment, not just calcium. The way they analyzed these samples were they were shooting photons to knock the electrons off to see what elements were present. And so they're looking at something called the X-ray photoelectron spectrum. Let's see if we have it. I think I did a search. I did this search earlier. So you put a sample in a vacuum chamber like this, and you can analyze the elemental composition. Let's see if we have some spectra. Not only can you do that, you can shine it in different parts of the sample to see how different parts of the sample behave. Yeah, well, what are you doing? You're just taking advantage of these allowed and forbidden states. These allowed and forbidden states gives you a unique fingerprint pattern, because the allowed and forbidden states, for example, a 1s orbital on hydrogen is not the same energy as a 1s orbital on helium. Actually, 1s orbital on helium is at lower energy. And so these are very unique energies. Since these are very unique energies, they're characteristic. We generate a fingerprint for specific elements based on their spectrum, so you can see it. So there's some kind of overlap and some kind of intermixing there that can make it difficult to analyze, but that's it. All right, so did that answer? Did somebody come up with the 99Z? Is it allowed or forbidden? Is it allowed? How did you determine if it's allowed or forbidden? Well, for one thing, I was thinking, well, to answer the next part is how many Z orbitals are there in the 99Z sublevel? This is allowed because the L, the biggest L that would be allowed in 99Z would be 98. How many letters are there in an alphabet? Yeah, 27, so this is gonna be allowed. But we don't count based on the alphabetical order. It's gonna be S, P, D, F. S, P, D, F, what comes next? A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. And so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So,
Did you be able to use P and S again?
no. After this one, we'd have to go to this kind of deal, double A, double B.
No, I know, but like in the middle, like after O, number 12. Would you be able to?
Oh, I see what you're saying. No, we can't use it. You're right. We can't use this one. We can't use S. That would screw things up. So we have to do an alternate once we get higher. So P, S, D. So just S and P. So that's going to offset it. That's good. You caught that. And so the lettering scheme would have to change. We'd have to use a different code. In fact, there's different ways we do the letters once we get to higher energy levels. But this would be the simplest. And so that would offset it by 2. So sorry about that. That would be so this should be a 21, Z21. So if a Z of 20, an L of 21, then M tells us what? M is going to tell us the number of orbitals. The number of orbitals is going to be given by 2L plus 1. And so it would be 42 plus 1 is 43 orbitals there in the orientations. Does that make sense? So something like that. Although the lettering scheme, I'm not sure about, not 100% certain about that lettering scheme because there are different ways to represent those orbitals with the lettering scheme. Okay, we'll take a break now. Thanks.